If a figure is a kite, then it is a quadrilateral. If a figure is a quadrilateral, then it is a polygon. Here's the thing. This is called the Law of Detachment, where if I say if A then B, and actually no, this is the law of syllogism. I apologize. The law of syllogism says if A then B and B then C, then A then C. You can just kind of skip it. So it's like if I were to drive to work, but on the way to work I hit up a Wawa, I could say like Mr. Perich drives to Wawa. Mr. Perich drives from Wawa to work. Why can't I just say Mr. Perich goes to work, huh? And so that's what we can do here. If a figure is a kite, then it is a quadrilateral. If it's a quadrilateral, then it's a polygon. So if a figure is a kite, put it in the chat. What do you think I'm going to write out? Or say it out loud. Do it before I do it. Then it is a polygon. Really? Lily's screen's not even loading. Oh, no, she's here now. Lily, you're good? She not talking. She all shy-ish. I don't see. Is that a thing? Is that like you're? Oh, yes. Oh, okay. Is ish saying yes? Is ish another way of saying yes? Okay, well, that doesn't help. What am I doing? Here we go. What are we doing today? We're going to talk about paragraph proofs and stuff called postulates, construct arguments, and whatever. Today is ish is kind of like right now it's 1:35-ish. Even though it's 11, or I'm sorry, right now it's 11:35-ish, even though it's 11:36. Are you catching what I'm throwing down? Okay. Look, it's Eminem's. He is a good rap guy. Writing proofs, writing proofs, writing proofs. This is the beginning of an awful, 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 awful thing called writing proofs. What a proof is I give you the beginning, I give you the end, and you have to fill in every single detail in between and explain what you did. So again, my story about me going to work, and let's just say Eastern work, because that's the only work that I go to that I actually drive to. And if I were to make a stop at Wawa, I could say like, prove that Mr. Perich, or prove, I guess I could say, given that Mr. Perich leaves his house, prove that he arrives at Eastern. How does he get there? And I could say like, okay, well, I hop on Yerger Road, which is where I live. And then I go on Bleem Road. And then I go on Pruss Hill Road. And then I go on Route 422. And then I stop at Wawa in Royersford. And then I leave the Wawa from Royersford. And then I get on 202. And then I get on Upper Gulf or something. I forget. All these different roads. And I have to prove everything in between. Well, in order for you to prove and explain your work in between, there are these things called postulates. Postulates, also known as axioms. And they're basically, a statement that's considered fact, and you don't have to really explain yourself. Basic ideas about points, lines, and planes can be stated as postulates. Here's a long list of a few of them. Gross. And we're going to come back to this page a lot. But I'm giving you 7 postulates. If you're looking at that and you're like, oh, poopy, am I going to have to memorize that? No, the answer is no. However, we might be getting into the territory that you're going to want to keep your book, like saved off to the side. The book that you go to ClassLink and you click on the Red McGraw-Hill and you click on the ebook. It may not be the worst idea to have that as a bookmark or something that you can easily pop up and won't take you forever to do. You know, I usually try to send you notes, and today I'm working on like 2 hours of sleep and I just plumb forgot. So here's our postulates. Postulate 2.1, through any 2 points, there's exactly one line. If I give you a dot and I give you a dot, you can only draw one line in between those 2 dots or connecting those 2 dots. That's obvious. Postulate 2.2, through any 3 collinear points, non-collinear points, I'm sorry, there is exactly one plane. That means if I were to put a dot here and a dot here and a dot here, I can draw a piece of paper or a, hold on. I could draw a piece of paper, or I could draw a plane, which is basically like a piece of paper to cover those 3 dots. Okay, that one may not be as clear, but it is fact. A line contains at least 2 points. That's like 2.1, but in reverse. A line contains at least 2 points. 2.4, a plane contains at least 3 non-collinear points. That's like 2.2, but in reverse. 2.5, if 2 points lie in a plane, so you have a piece of paper and you put a dot on the piece of paper and you put another dot on the piece of paper, then the entire line connecting those points lies on a plane. That makes sense. If I were to take a piece of paper and go put a dot on the one piece and a dot on the same piece of paper, and I draw a line, that line's going to end up being on that piece of paper. It's not going to jump off the paper. That's not how lines work. If 2 lines intersect, this is 2.6. If 2 lines intersect, then they intersect at exactly 1 point. That makes sense. If I take this line here and this line here, which is an X-Acto knife, it's only going to touch each other at one spot. Okay. Last but not least, if 2 planes intersect, then their intersection is a line, one line. And that's like if I were to take the green piece of paper and the blue piece of paper that you see and try to force the one into the other, where those 2 planes intersect is at a line. So that's very hard to visualize, very hard to understand. Let me explain how the figure illustrates that each statement is true, then state the postulate that can be used to show each statement is true. So what's going to happen is I'm going to see a sentence, I'm going to explain why it's true, and then I'm going to go back 2 slides, and I'm going to, wrong way. And I'm going to go back and pull up the reason why we're allowed to say that. So, problem 1. This is what we have. This is what we have, just in case no one's understanding the picture. What we have is we have a box, a rectangular prism, if you will. And on the front of the box, on the front of the rectangular prism, I have the dot A on the side, and I have the dot D on the corner, and the dot C on the bottom, and the dot E on the bottom corner, B in the middle. On the side of it, I have A, and I have these lines poking up through the sides and out the sides. Okay, so that's what I have. Plane P and Q intersect in line R. Explain how the figure illustrates that each statement is true. So these are true statements. I just need to explain, and I'm going to use words and not have to write out, because you know what happens when I try to write things out. I'm just going to explain using words why that's true. P and Q, so this is P. Plane P is this side here. So if you're thinking about a box, which let me get a box quick. I'm back. So this is my Paul George NASA shoes. This is part of my extensive t-shirt shoe collection, sneaker collection. That's how I handled my midlife crisis. Instead of buying a car, I just bought a bunch of shoes. I have plane Q, which according to this picture appears to be the front of the box. And I have plane P, which according to the picture appears to be the side of the box. So this is Q. This is P. This meets this at that line there. So this plane meets that plane at that line right there. So that makes sense to me because it's kind of like, you know, these two fold over right around here. That's my line where the two planes intersect. What postulate was that? That was postulate 20 or 2.7 because you have two planes intersecting at a line. So this is postulate 2.7. Let me, there's a bit of a lag. Let me get out of this thing. All right. Lines R and N. So R would be like if you go, R would be like one of the lines. So I didn't mean to make that line there, but that's line R. So this corner or that corner, it really doesn't matter how you view it, is a line. Okay. The corner here, the bend is line R. And the bend at the bottom is line N. So here's R, here's N. They meet right there at that corner D. Okay, so that's a line intersecting another line at a point. So that makes sense to me. That makes sense. If I go up, I need the postulate that says two lines intersect at a point, and that appears to be 2.6. If two lines intersect, then their intersection is exactly 1 point. So that's 2.6. Again, and maybe I didn't make this clear, you're not memorizing these. You're not memorizing them at all. Okay. It's just that you should be able to go to your book and say, that's postulate 2.6. Line N, which is this line down here, contains the points C, D, E. That makes sense. If I were to, along the corner of this bend right here, if I were to put a dot right there and say that's going to be dot D, and if I were to draw a dot right there and that's going to be dot C, and if I were to draw a dot right here and that's going to be E, all three of them live on the corner. So that makes sense. What I need is the postulate that says that a line contains at least 2 points. So let me see. A line contains at least 2 points through any 2 points. Nope, that's not it. That's backwards. A line contains at least 2 points. That's 2.3. So how do I know it's 2.3 and not 2.1? Let's go back. How do I know it's 2.3? Because some might be like, is it 2.1 and 2.3 the same thing? No. 2.1 says if I give you a dot and I give you a dot, I can draw one line. 2.3 says if I give you a line, I can draw as many dots as I want. It depends on what you're given first. So 2.3 starts with the line, and this problem here started by saying line, which means that's 2.3. So be very careful making that distinction because it's very, very, very easy to get something like that backwards. Plane P. Plane P is the side here. So this is plane P. Contains A, F, and D. All right, so this is what it looks like on the notes. I have P is the side, F lives smack in the middle, A lives on a corner, and D lives on the very corner. So I guess I should say A lives on like where it bends. So that would be like if this is P, if this is the side P, if I put a dot right there and call it F, that would make sense. If I were to go up here and put a dot right there and call it A, that still lives on this side, lives on the edge of the side. It's like, no joke, I grew up living in a house where the school district was separated by going through the yard, but the house was on the Pottstown side of the yard. So I went to Pottstown. So it's kind of like, even though it's right there on it, it's still on that side. And D would be like the bottom corner. So same thing. So F lives really on it. A lives on the side here, and D lives on the very corner. So it starts out by saying plane P. I need the postulate that says a plane has at least 3 non-collinear points. A plane has at least 3 non-collinear points, and that would be 2.4. Last but not least, line N is in plane Q. So line N lives in plane Q. So that's like saying, here's plane Q, there's my line N. So this one's not as clear, so let me look at my pictures. Probably 2.5. If 2 points lie on a plane, then the entire line containing those points lies in the plane. So this would be 2.5. And it's not clear by the way it's worded. But if you look, it gives me 3 points. Boop, boop, boop. So this plane has these points and the line N living on it. So it's not as clear, but this is line 2.5. I'm sorry, postulate 2.5. Postulate 2.5. And again, this is my my PG3 NASA shoes, all silver version. They're over there. If you look right above, that's them right there, right next to my brand new 720 818s that I just got the other day. So I see there's a little bit of confusion in the chat. And again, I realize I'm trying to teach you a 3D land through a computer. So there is going to be confusion, and I understand that. And my advice is that let's try to be patient and rewatch these videos if you're still not sure, and we will review over and over and over and over and over again. Before we're going to have a quiz on this stuff on like Monday, but before we even get there, we're still going to use tomorrow to keep learning this lesson, and Friday is going to be a day of review, in which case I probably ask you to watch videos like I did this morning. So I understand if you're confused. I don't blame you. You're used to being really good at math, which is numbers and stuff, and all of a sudden I'm like, look, this line contains 3 points, and you're like, what the heck is this? I understand, but I will hold your hand and make sure that you're not lost. Not literally. I can't even do that if I wanted to. All right, never mind. Determine whether each statement is always, sometimes, or never true. Okay, so a statement like Mr. Perich wears glasses is sometimes true because look. A statement like Mr. Perich cannot grow hair atop his head. Oh, good, Camilla. Yes, Mr. Perich uses shampoo. That is actually never true because why would I use shampoo? I don't need shampoo. Whereas Mr. Perich uses bar soap without a wash rag. That is always true because why the heck would I use my own bar soap and have a wash rag? What a waste. I found out that it's very WHITE to use bar soap and not have a wash rag. So some of you are like, that's disgusting. Well, it is what it is. Determine whether each statement is always, sometimes, or never true. If the plane, so I'm going to draw a picture. A plane contains a line and a line contains a point, then the plane contains the point. If a plane contains a line and a line contains a point, then the plane contains the point. What if I drew a line like way the heck over here? Because it says a line, not the line. I can make it so that it is sometimes true, and I could draw a picture over here so that it's not true in this case. So this is a sometimes. Because I can draw a plane. I can draw a piece of paper, and on that piece of paper, I can draw a line with a point. I can also take my piece of paper, crumble it up, throw away, and go up to my whiteboard and draw a line with a point on it and say, look, that line's over there now. So that's not on the piece of paper. Sometimes true, sometimes not true. So sometimes. A line contains 3 non-collinear points. Non-collinear means not on a line. So can a line contain 3 points not on a line? No. The phrase itself is contradictory, and Santi jumped in right before I could write it out. So good. Okay, that's basically saying Mr. Perich's hair. Just stop right there. Stop right there. Line R contains only a point B. Only a point B. So let me see. So that's true. You bring up a good point. Line R contains only a point B, but I can also have it contain C. So this is another sometimes. Although some people might argue never, because a line has to have 2 points. But I think I can safely say that this is a sometimes. I might be wrong on that. I don't know. I can argue it, though. In figure AK, is in plane P, and M is on NE. So this is what we're looking at. I don't have any pieces of paper on me, but what I would do is I would take a piece of paper. Here's my piece of paper. I would draw, this piece of paper is called P. I'm going to actually put it this way. This piece of paper is called P. I draw a line on the piece of paper called AK. I take this X-Acto knife here and I stab my hand with it. The X-Acto knife is called ME. Up here is M. Down here is E, and my stab wound is called N. I'm sorry, Paul. I sometimes have to use violence to make my point, but this is what I have. My hand is called P. I draw a line on my hand called AK. So there it is. There's my AK. Okay. I stab my, so there's A, there's K. All right. I stab my hand, and the stabbing device is called ME. My stab wound is N. Okay. Boy, does this hurt. M, K, and N are coplanar. State that the postulate that can be used to show each statement is true. So M, K, and N are coplanar. I have 3 points on a plane. So if I'm given 3 points, they can live on the same plane. So that would either be 2.2 or 2.4, but I'm given the 3 points. So this is going to be 2.2 because of the way it's worded. 2.2 starts you out with points. 2.4 starts you out with a plane. So if I start out with points, this is 2.2 because of the way it's worded. My hand hurts. Psych. Psych no. Psych no. So line NE. So here's my stab wound is N. E is down here. Line NE contains the stab wound and then the top of the line. So I have a line that contains 2 points. I have a line that contains 2 points. Nope, because that starts out with the points. That starts out with the line. A line contains at least 2 points. So this guy is 2.3. So again, I start out with the word, a line, and I compare that to the one that says a line contains whatever. Okay, here's my hand still got a hand. N and K, so I have 2 points, are collinear. So I can draw a line connecting N and K. So I have 2 points, and if I have 2 points, I can draw a line. So let's see what that is. If I have 2 points, through any 2 points, there's exactly one line. This one's 2.1. 2 points becomes a line. And then I start out with 2 points, 3 points, N, A, and K, and then I end up with a plane. So 3 points becomes a plane. 3 points becomes a plane. Going the wrong way. So I need the plane one. Through any 3 non-collinear points, there's exactly one plane. So this is 2.2 again. Yep. So if you're looking at 9 and you're looking at 12 and you're saying they're like the same thing, just worded differently. Yup. Problem 10 was 2.7. And 11 is 2.1. 9 and 12 are the same type of problem, but are worded differently. And the only difference is the fact that 9 doesn't use the word points. They just tell you 3 letters, which means they're points. And 12 uses the word points. But I go in the order in which I'm given, where it says point, point, point are coplanar. So I go to the postulate that says 3 collinear points, non-collinear points are coplanar, or whatever it was. So yesterday we talked about postulates. Yesterday we talked about, all the rules that justify what we're allowed to do. And so we had this big list. I think it was slide 4 was the list. And then so we were given a bunch of rules and stuff like that. We were given a bunch of statements and we were asked, why is this true? Well, we could look at the statements and the way the statements are and use those statements to prove that our little rule that we were given, or a little question that we were given, is a true statement. Now we're going to do what's called a full-blown proof. And there's 2 types of proofs that we're going to start out with. To prove a conjecture, you use deductive reasoning to move from a hypothesis to a conclusion of the conjecture you are trying to prove. This is done by writing a proof, which is a logical argument in which each statement you make is supported by a statement that is accepted as true. A flow proof uses statements written in boxes and arrows to show the logical. Basically, it's a flow chart. If you've ever seen a flow chart, a flow proof is a flow chart where you have to explain why you said what you said. The reason justifying each statement is written below the box. This type of proof allows you to see each statement is deduced from the other statements, blah, 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 blah. All right. This is how we write a flow proof. And this is how we write a flow. I'm going to rap. Just kidding. I'm not going to do that. Write the given statement in a box in the word given underneath. No, Santi, no. Create a deductive argument by forming a logical chain of statements linking the given to what you are trying to prove. Write these statements in linked boxes and justify each statement with a reason. So basically, I have to say, I am given this piece of information, and then it goes to a box. And then I explain why I did what I did. And then it goes to another box. And then I explain why I did what I did. And then once I'm done, I state that I have proven what I've done. So here's some statements that we're going to come back to every now and then. Again, these are not things you absolutely have to memorize, but it's stuff that you've seen before. If I add something to both sides, it's called the addition property of equality. If I subtract something from both sides, it's called the subtraction property of equality. If I multiply something from both sides, it's called the multiplication property of equality. If I have to divide something from both sides, it's called the division property of equality. If I have something equals itself, and it's called the symmetric property of equality. The transitive property of equality is the law of syllogism. If A equals B and B equals C, then A equals C. If I substitute something, that's called the substitution property of equality. And if I distribute something, it's called the distributive property of equality. Now, you know all of these exist, and the one that you probably would look at and be like, what's even the point of reflexive? You'll see. What's the point of transitive property? Or like we did the law of syllogism, which says if A then B and B then C, then A then C, why do this? Well, the law of syllogism is not equality stuff. It's this specifically has to do with solving algebraic equations. So like if I had A plus 3, A plus 3 equals 9. Wow. Oh, you know what? I know why. I know why. I know why. This is laggy. That's not why. Where's I don't know why this is laggy. My computer's or the internet's been very slow. I blame it on the fact that I keep checking on election results every 5 seconds, like I'm doing right now. No. All right. So if I have, and let's try this again and see if it'll look right. If I have A plus 3 equals 9. If I'm going to be asked to solve this and justify my work, I would subtract 3 from both sides, and that's using the subtraction property of equality. So if I was asked to solve this, solve A for A, I would multiply 3 to both sides, and so that's using the multiplication property of equality. So what we're going to do is we're going to do what's called flow charts, and we're going to be given pieces of information, and we have to use these phrases here to explain everything that we've done along the way. Okay? So let me close a few more. This is very laggy, so let me close a few more things that I probably don't need anymore. I think that should maybe do it. We'll see. I can't close the Google Meet, then I won't see you guys anymore. How sad would that be? All right, so complete the following flow proof, and I have to fill in those blanks. All right, so here we are. I'm given 5x minus 12 equals 8. I have to prove x equals 4. So this is the flow. So the flow proof, the math stuff behind it is me showing every single step. Underneath the flow part, I have to justify with one of these guys down here. Except for in the case of this part, instead of giving one of these guys, it looks like I have to come to my answer. Okay, so I start out with 5x minus 12 equals 8, and then it turns into 5x minus 12 plus 12 equals 8 plus 12. First off, in every single proof, you always write out the given. Always write out the given, and your explanation for that is the phrase given. In every single, my gosh, in every single proof that you have to write out, you always write out the given first, and you always explain why you're doing that by writing out the word given. In the second statement, it appears, and you could use your own words right now in the chat, or you can unmute yourself. It appears that they did what to both sides? Add 12 to both sides. So if you're adding 12 to both sides, then the explanation behind B is you are using, and this is going to be fun, you are using the addition property of equality. And yes, I write out the entire thing, even if it looks awful, because there's a severe lag on my Chromebook today. the addition property of equality. Questions? Now what? Oh, okay. Okay. So now I have 5x equals 12. And I have to describe why I have 5x equals 12. Well, if I added 12 to both sides, I'd like to argue that I don't need to do that. I don't need to write it out. Let's skip C for now. What are you going to write D for D in the spot that says D? X equals 4 is correct. For C, I don't know why we would have to do the explanation. Because I explained what I did in B. C is not the given. C is, I mean, for C, we could just say, like, how did we get from here? I mean, let me get my mouse. Let me get my mouse. The reason why we explained this is we had something brand new, and the something brand new that we did was add 12 to both sides. And the reason why you're allowed to add 12 to both sides is the addition property of equality. By adding 12, you got that. So we could say for C, combining like terms. You can say for C, you added, but I'm just going to say for C, combining like terms. There's probably a better way to say that, but there's nothing wrong with saying that. Oh my gosh. That's supposed to be a B. Combine. I'm just going to write out fast and see what happens. See what it looks like. Combining like terms. Perfect. Okay. That's a flow proof. And again, thank you, Santiago. Again, what you're doing is you're explaining each step. The first step is always the given. The second step, I added 12 to both sides. That's the addition property of equality. The third step is what I got after I added. So what did I do there? Well, I combined like terms. And the fourth step is division property. But what am I supposed to put up here? Well, you're supposed to put your answer. Or you could probably say x divided by 5, or I could do the divided by 5 things here. I think this is perfectly fine. We're done. We're very rarely going to use flow proofs. Very rarely. But this is just the beginning of proofs. This is another flow proof. So this is going to look absolutely terrific when I try to write it all out using boxes and stuff. I'm actually going to do something that I might regret later, and I'm just going to completely close all of these things up here. All these things that I was purposely saving for my other classes, I'm going to close every single one of them, which means I'm going to have to get them all back. I can't close that one. I'll close that one. All right. Hopefully that fixes the lag. I only have a few things running now. Write a flow proof. So the first thing that you're going to do, yeah, that seems to be much better. The first thing that you're going to do is you're going to write the given inside a box. Okay, and the given that I have is line JK, just kidding, is congruent to line KL. And my reason for that is given. I have to prove that y equals 9. So what am I going to do first? I'm going to substitute instead of jk, I have 15. And instead of KL, I have 3y minus 9. Now, I used a keyword there. Type in the chat what my keyword was when I went from the left box to the right box. I said a keyword. Substitution, no one said. So my reason for going from JK to 15 and KL to 3y minus 9 is because I substituted. So this is the substitution property of equality. Substitution property of equality. What's my first step? Either put it in the chat or write it. What's my first step in doing this? In doing this problem?
Subtract 9 from both. No, add 9 from both sides.
Add 9 to both sides. So I'm going to actually good, Paul. I'm actually going to write. I'm going to write that out like the way that they wrote it out, even though I might do it differently. No, I'm going to write it out the way I always write it out. Why am I going to change to adapt to them? I'm going to put add 9, and I'm going to put add 9. Okay, and that was the addition property of equality. Property brothers of equality, am I right? Somebody put something in the chat. I'm sure it's LOL. Funny. I'll take it. Once I do that, I end up with this box. On the left side, I'm going to have what number? And on the right side, I'm going to have what number letter combination? Or essentially, what am I going to type in this thing? We are not at y equals 8 yet. We're not at y equals 8 yet. We will be. I added 9 to both sides, which leaves me with blank equals blank blank. 24, somebody said, equals 3y. Good, Santiago. The reason why I got that is I combine like terms. I am going to be lazy, and I'm just going to write out combine like terms because I added stuff. Now what I need to do I'm going to continue flowing over there. Flowcabulary, remember that? I'm going to show the process of doing what to both sides. And you can unmute yourself or you can write it in the chat.
Division?
Division. So I'm going to show me dividing both sides by 3. And take a wild guess the name of that property of equality. The what property of equality? Division property of equality is correct. So I will write out division property of Why did I put an F? Property of equality. This literally is the same handwriting as my kindergarten children's handwriting. It's embarrassing. I then can say what equals what. Close. See, I'm going to be super picky. I'm going to be super picky, and it's going to drive you bananas And if you said that, Santiago, I would never fault you for it because you're not wrong. You're fine. But if I'm going to be a math teacher like I am and be as super picky as I know I am, I'm going to write out 8 equals y. And I'm going to say 8 equals y because I divided both sides by 3. I combine like terms. Is that exactly what my proof says I have to do? Is that exactly what proof says? Is it? Is it? No. Because prove says the reverse, as Santiago said. And so I'm just going to flip it around. And the process of flipping it around had a name. And I believe, I want to say it's the symmetry property of equality. I just want to make sure. Symmetric property of equality. The symmetric property of equality says if A equals B, then B equals A, which means I could just flip it. So this is the symmetric property of equality. And now I'm done. So that's what a flow proof is. In the end, it's pretty. I mean, I guess you could say my friend Edgar and Alan would like this, right, Paul? Okay. Edgar Allan Poe. There's a little theorem called the midpoint theorem. The midpoint theorem states that if M is the midpoint of AB, then AM is congruent to MB. So let's talk about paragraph proofs, also known as informal proofs. If you're given something given, and instead of doing this flow chart, I were to use words, like I would actually write out the words, I am given JK is congruent to KL. My first step is to subtract. Oh, no. My first step is substitute 15 equals 3y, and I use the substitution of minus 9, and I use the substitution property of equality. Then I add 9 to both sides, and I use the addition property of inequality. And then I combine like terms to get 24 equals 3y. And then I divide both sides by 3 using the division property of equality, which gave me a equals 9 because I combined 8 equals y because I combined like terms. And then I flip them to get y equals 8 using symmetric property of equality. That's a paragraph proof. It's literally the same thing, but instead of using this beautiful little thing that flows, I actually write out the paragraph or the informal proof. Okay. And the way that I do that is almost the same exact way. Write out your given and proof statements. So I am literally rewriting this guy out right here. I'm just writing that out. Step 2 is I draw a diagram and I label any figures. So that's this part right here. I'm actually drawing that. So far, it's no different. Okay, it'll give me a sentence and it'll ask me, given something, prove something. And so I write that out and I draw that out. My third step is I just create a paragraph of things that I'm doing and reasons that I'm doing them. Okay, I'm going step by step by step. And with every mathy thing that I do, I explain myself using whatever property or whatever reason that seems to make sense. And then when I'm done, I state what I proved. So when I'm done, I write out y equals 8. And I'm in good shape, which I rhymed. So what we're going to do is we're going to watch a video that you probably watched this morning, but it would never kill you to watch it again. And plus, it always gives me one more YouTube view. And boy, do I need that sweet YouTube money. Boy, do I need it. I'm going to mute myself and we're going to watch it. Okay, on today's episode of Pen and Paper, let's discuss the old tried and true paragraph proof. A paragraph proof is just a very nitpicky way of explaining why something works the way it does. This is our paragraph proof, given that C is in between A and B, and segment AC is congruent to segment CB, write a paragraph proof to show that C is the midpoint of segment AB. The first thing that we're going to do is we're going to write out our given and proof statements in this form. We're going to say the phrase given, and we write out what we're given. C is between A and B, and segment AC is congruent to CB, segment CB. So we're going to say that. Given C is between A and B, and segment AC is congruent to segment CB. Okay, we write that out. Also, we write out what we're trying to prove. Prove C is the midpoint of line segment AB. Okay, so we write out our given pretty much exactly as it's written to us. We write out our prove pretty much exactly how it's given to us. The next thing that we're going to do is we're going to draw a picture for anything that we would need to. In this case, it tells us that C is in between A and B, and it tells us that AC is congruent to CB. So let's draw that picture. I have line segment AB, or at least I have 2 points A and B. I'm given that C is in between them, and also that AC is congruent to CB. So C is in between them. AC is congruent to CB, and I'm using those little tick marks to show that those two line segments are congruent or equal in measure to each other. Now I begin my proof. We're going to write out our proof. Like I said, we're just going to be very nitpicky and give every possible reason that we could. So I could say something to the fact that I have to show that C is the midpoint. So I'm kind of going to not work backwards. I need to show that C is the midpoint. If C is the midpoint, then I have to show that these two are equal in length. And how can I show that they're equal in length? Well, I can show that they're equal in length because that says so. And I also need to show that C is in between. So what I'm going to do is that if C is in between if C is in between A and B, and also they are collinear, then AC plus CB equals AB. If AC is congruent to AB, segment AC is congruent to AB. I'm sorry, CB. Ugh. CB. Then, by definition of congruence, this is me giving my reason. By definition of congruence, AC equals CB. So this is what I did. I'm breaking things down. I'm literally taking the two parts of information that I was given in my given. C is in between A and B. Well, what does that mean? Well, that means they're on the same line. And then AC plus CB is going to equal to AB. All right. Then the second part that I'm given is that AC is congruent to CB. Well, what does that mean? Well, if AC is congruent to CB, then because they're congruent, AC's measure is equal to CB's measure. Okay. So what else do I need to prove? I guess that's really all I need to say. So by definition, of midpoint, just making sure you can see everything, since AC is equal to CB, then C is the midpoint of angle of line segment AB. Whenever I'm done my proof, I like to put a little box next to it. That just means I'm done. Okay, so again, it seems like we're being nitpicky. But I need to find a way to explain what I'm doing, and every time I give a little piece of information, I have to explain what I'm doing. I have to say, well, because of the definition of congruence, because of the definition of midpoint, blah, blah, blah. Okay, I think that'll do it. Bye. Echo, 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 echo. All right, so if you look at my camera, I've moved to pen and paper format because there's absolutely no way I'm going to successfully write anything on my Chromebook right now. I am to write a paragraph proof, okay? And I'm given a picture and I'm given a few words. So this is what I do. I'm going to rewrite that out. Let me use a black marker. I'm going to write out. I just want to make sure that you guys can see everything. I think you can. Given y is the midpoint of xz. Also, I'm given that xy is congruent to wy. I need to prove that wy is congruent to yz. I've heard of jz, but yz, that's different. That's a different wrapper. I'm not on whiteboard, Paul. I'm going to draw my picture. I'm going to draw it here. X, Z, Y, W. I was told that Y is the midpoint and that XY is congruent to WY. So that's what I'm told. I need to prove that XY, I'm sorry, that WY and YZ are also equal to each other. All right. Okay. Okay. Since Y, well, we are given that Y is the midpoint of XZ. So, by definition, of midpoint, we can say that since Y is the midpoint of XZ, we could say that XY is congruent to YZ. XY is congruent to XZ. Okay? Does that make sense? Zoom into screen so you can see better. Is it blurry? Or are you telling other people?
I think those of you who are wondering, Santi's just helping everybody out. Click on my screen. I mean, everything that's on the shared part that I'm presenting from my Chromebook is now on here. So you don't need to see anything from my Chromebook. So yeah, click on my screen and zoom in. So what I did first, just your name blocks some of the work on the bottom left. I don't know. All right, so given y is the midpoint of xz, I was able to say we are given y is the midpoint of xz. So by definition of the midpoint, we could say that xy is congruent to xz. Since, and watch me, well, how do I want to write this out? I might be super picky math teacher, but I don't think I have to. Since xy is equal to xz and congruent, and what else were we told? Xy is congruent to wy. See what I did? I said xy is equal to xz. I also said xy is equal to wy. Then, using the transitive property, if xy is xz and xy is wz, I'm sorry, wy, then xz is the same as wy. And is that what I want to prove? That's not what I want to prove. What did I do wrong here? Oh, I know what I did. 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 We are given that y is the midpoint of xz. So by definition of the midpoint, we can say that wy is the same as yz. That's a stupid typo by me. xy is the same as yz. So since xy is the same as yz, sorry about that. Since xy is the same as yz, and y is the same as wy, then by the transitive property of equality, we could say wy is the same as as yz. If xy is the same as wy, and xy is also the same as yz, then wy and yz are also the same. So that's it. I'm done. Okay. I have a feeling that wasn't fun. So this might be something tomorrow afternoon where we're just going to do a couple paragraph proofs to make sure that we're a little bit better. But we are literally out of time. We have 1 more minute to go. So I'm going to end the chat. I suggest you do too. No, of course you do not write this. That was a bit confusing because I did screw up by making that the wrong letter. And so my blunder kind of threw people off. So we might have to do more of these tomorrow afternoon. No big deal. That's part of being a student. The first type of proof that we're going to go over is a flow proof. A flow proof is when I need to give you evidence that I can rap well. Oh, boy. No, I'm kidding. A flow proof is like a flow chart, but with, proof and stuff. So let's take a look at what we have. Given the triangle pictured, I need to prove that x equals -8. So, all right. So let's start out with what I have. I have in my box, I have triangle, triangle. I don't even have a name for it. I'm just going to say triangle pictured. Triangle pictured. All right. And my reason for that is the given. You always put your given in the first box. What do I know? I know that if it's a triangle, I know that 65 plus 40 plus x plus 83 equals 180. How do I know that? Well, I know that because of the definition of a triangle. Or we could also say there's this little thing called triangle angle sum. Again, if this was a test and if I were to give you a pop quiz on this and ask you to explain what you did, I wouldn't expect everybody to pull out the fact that there's something called the triangle angle sum. It's also called the interior angle sum. All I know is I would expect you to show, like, you know, you would do this the way you would do a regular math problem. The way you would do a regular math problem is you would say that plus that plus that equals 180. Now you're just explaining yourself and you're putting them in boxes. All right, the next box that I can create is the fact that I have 65 plus 40, which is 105, plus 83, which is 188. 188 plus x equals 180. How did I do that? Well, I combined like terms. Now I'm going to take my chart and I'm going to bring it over here because I like to work left to right. Not that that's what you have to do, but that's just what I'm going to do. And what I'm going to do is I'm going to subtract 188 from both sides. So I'm going to write out the original thing, and I'm going to subtract 188 from both sides. When you subtract a number from both sides of the equal sign, it's called the subtraction property of equality. No matter what I do, it's going to be kind of blurry on the side. That's a bit blurry. That's better. When you do that, you get x equals -8. And I do that by combining like terms again. So I'm done. I mean, my job was to prove that x equals -8, and I did. I did it. I did just that. And a flow chart or a flow proof is the same thing as making a flow chart with explanations along the way. Okay. Okay. I'm just letting that sit there, let it marinate for a minute before I go to my next flow proof. Make a flow proof. I've heard of foolproof, but flow proof, that's different. Boy, am I good. I'm on fire today. I'm on fire. Someone call the fire department because I'm roasting here. Oh, man. Given M is the midpoint of AB, segment AB, AM equals 2x plus 4, and MB equals, there's a lot there. So I have a lot to pack into my given box. So I have M is the midpoint of AB. I also know that AM is 2x plus 4. I also know that MB is 4x minus 2. I also know that AB is 20. That's funny. I only have 6 of those. So that's what I have. That's the information that I have. I should be able to look up at my picture and say, all right, well, look, if M is the midpoint, then I know that AM and MB are going to be equal to each other. So that's what I'm going to say next. I'm going to say that AM is equal. Oh, you know what I forgot to do? I forgot to say given. Oh, boy. I know that AM is equal to MB. Now, there's 2 different ways that I could have done this, and this is just the first thing that I did. This is just the first thing that I did. The 2 different ways that I could have done this is I know that if AM equals MB, then I set these guys equal to each other. That's the one thing I could have done. The other thing that I could have done is AM plus MB equals 20. So there's 2 different ways that I could prove that X is 3, but this is what I'm doing, and I'm sticking with it. So the reason why I could say that AM equals MB is that's the definition of a midpoint. A definition of a midpoint says that if you have a point that is in the middle of a segment, it cuts that segment into 2 equal parts. And by M being the midpoint, it cuts AB into 2 equal parts. So what I can do now that I've said this is I can say that if AM equals MB, I could say that AM is 2x plus 4. That's going to equal MB, which is 4x minus 2. Why am I allowed to do that? Because I substituted, and this is called the substitution property of equality. If I replace something with something else, it's called the substitution property of equality. This all goes from those rules that were written down that I'm taking it from. So like that's why I said subtraction up here that you can't see anymore. All right, so what can I do now? Well, if 2x plus 4 equals 4x plus 2, I can get rid of, let's do 2x from both sides. So what I'm going to do is I'm going to subtract 2x from both sides. By doing that, I employed the subtraction property of equality. That makes it become 4 equals 4x minus 2. How do I know that? Well, because if I take what I said was 4 equals 2x minus 2. How do I know that? Well, if I take 4x minus 2x and combine those like terms, I end up with that. So allow me to write out this guy again, 4 equals 2x minus 2. And in order to get x all by itself, I add 2 to both sides. What is that called? The addition property of equality. Addition property of equality says I can take any number and add it to both sides of an equal sign. When I combine like terms, I end up with 4 equals 2x. I keep doing that. 6 equals 2x. 6 equals 2x. And I did that by combining like terms. Oof. Let's keep flowing. Let's keep flowing. If I take 6 equals 2x and divide both sides by 2, I'm doing what's called, sorry about that. I'm doing what's called the division property of equality. Didn't give myself a whole lot of space to do this problem. Shame on me. That becomes 3 equals x. Why? Because I combined like terms. And did I prove what I wanted to prove? Yes, but no. I have 3 equals x, which I'm allowed to turn into x equals 3 because of the reflexive property. Float proofs are not fun at all, unless you have a sick brain and there's something wrong with your brain. But there it is. It's a challenge, and it's just a way for me to explain what I'm doing. But the long and short of it is I'm just looking at everything. If I take my fact that I have up here, right, and I just show all of my steps and explain what I'm doing, that's what a flow chart is. Great. Now that I feel comfortable about that, let's do something new. Not new, but something that you've seen before. This is probably the worst of the two. The paragraph proof. Given that M is the midpoint of PQ, write a paragraph proof to show that PM equals MQ. Okay, well, what am I given? I am given, and that's how I start a paragraph proof out. I write out what my given is. I am given M is the midpoint of segment PQ. And what I have to do is I have to prove that PM, post meridian, equals MQ. All right. So I don't know why I started out with so. If M is the midpoint of PQ, then PM is equal to MQ by definition of a midpoint. Segment PM is congruent to segment MQ because line segments that are equal in measure are congruent. And that's it. It seems too obvious. It seems too easy. But sometimes that's what paragraph proofs are. Paragraph proofs are like, hey, I'm going to give you this, and you need to show me that. Well, you could be like, well, if M's the midpoint, then that means these two guys are equal to each other. And if they're equal to each other, then they're congruent to each other. Done. That's it. That's it. Let's take a look at one more. It's hard for me to see that. Given that angle BA, I'm sorry, not angle, that line BA is perpendicular to line BC, Okay, or yeah, is it line? It's actually ray. Given that ray BA is perpendicular to ray BC, prove angle 3 and 4 are complementary. Okay? So I have the given. Let me just write it larger so you can see it. I'm given the fact that BA is perpendicular to BC. Now, usually, you know, and I remember a couple weeks ago, somebody saw that sign and said, what does that sign mean? It's perpendicular. Okay, so now I actually get to really explain what it means. I need to prove angle 3 and angle 4 are complementary. So I need to use words to prove that. All right, well, by definition of perpendicular, then BA and BC, and I'm going to make those line segments, BA and BC intersect to form 90-degree angles, or a 90-degree angle. Angle ABD plus angle DBC equal angle ABC. Because they share a common side. So this is what I'm doing. This is how my brain works. I just showed that that angle and that angle intersect to make 90 degrees. I'm saying that that guy and that guy adds up to 90 degrees. Well, adds up to something. Adds up to ABC. Angle ABC is 90 degrees because they are created by BA and BC. So now what I'm doing is, this is what I said so far, these two intersect to make 90 degrees. These two angles right here add up to each other, or add up to ABC, and ABC is 90 degrees. So by substitution, angle ABD plus angle DBC, angle ADB plus angle DBC is going to equal ABC. Nope, ABC is 90 degrees, so equals 90 degrees. Also, angle, 3 plus angle 4 equals 90 degrees by substitution. What does that mean? Angle ABD is 3, so I'm turning ABD into 3. Angle DBC is 4, so I'm turning DBC into 4. So if angle 3 and angle 4 are 90 degrees, then by the definition of complementary, Angles, angle 3 and angle 4 are complementary, because complementary is 90 degrees. Who would have thought that when you guys were like really smart and were able to be advanced and stuff like that, that you would be involved in a math class that involved a whole lot more writing than math? Oh,